Hi everyone, thanks for coming to this talk on subsampling suffices for adaptive data analysis. We're going to start with a very simple setup with the goal of motivating the entire field of adaptive data analysis. So suppose Alice is some data analyst who wants to know something about what sorts of pets people own. So she gets a database of pet owners and what pets they own, and she may be interested in things like what fraction of people own dogs or cats or birds. And so she runs these queries and she gets responses from her database that in the database, 60% of people own dogs. And similarly, cats and birds, she gets other numbers. The important thing is that Alice can now conclude something about the entire distribution. She can conclude that with high probability, the true fraction of people who own dogs is between, say, 59 and 61%. And this is using classical techniques that are fairly simple. At this point, Alice might have an idea. Oh, I've seen that many people own dogs and many people own cats. I wonder how many people own dogs and cats. And so she runs this query and she gets a response that in the database, 25% of people own dogs and cats. Unfortunately, she cannot conclude that this 25% is close to the true distribution. And the reason is that the classical techniques break down. Alice first saw in the dataset that many people own dogs and many people own cats before making the decision to make this query asking how many people own dogs and cats. So the sample is not independent of her choice of query. This problem was formalized almost a decade ago. And formally, we want to know what sorts of guarantees can we make, ensuring that the responses Alice gets will generalize to the entire population, even when she chooses queries adaptively. We're going to start exploring this with two motivating questions. So if my goal in life is to ensure that the queries Alice makes, the responses she gets, will be indicative of the responses she would get on the entire population, a first question is, what sorts of queries can we allow? One useful example of a class of queries are statistical queries. These queries are specified by a function mapping a single data point to a number between 0 and 1, as well as a tolerance parameter. And Alice would be happy with any response that is within plus or minus epsilon of the true population mean of her query. One example of such a query is asking what fraction of people own dogs, and the function here would just take in a single person and output the indicator of whether or not they own a dog. So if the true population mean were 60%, Alice would be happy with anything between 59 and 61%. And typically we allow these queries to be adaptive, so after getting a response to the first query, Alice can ask, some other statistical query. The reason this framework is useful, the SQ framework, is because most algorithms in data analysis can be cast as a series of adaptive statistical queries, including most algorithms for supervised and unsupervised learning. So if Alice has some tasks she wants to solve, she can likely cast it as a series of SQs. So if we can handle adaptive SQs, we can handle many types of analyses. A second question is, once I pick the particular class of queries I want to answer, for example, statistical queries, how should I answer them? And at first glance, it's not clear this is an interesting question. For many classes of queries, there's an obvious thing to try to answer them, but it turns out that the obvious thing can fail when the queries are asked adaptively. So for SQs, when Alice wants to know the mean of some function phi on the distribution, but she's only given the sample, the obvious thing to do is to compute the empirical mean, to use the value of phi evaluated on her sample. Then she can repeat this process. After getting this response, she asks a new SQ. And unfortunately, this idea of using the empirical mean can fail badly. Even if Alice only asks two queries, she can learn so much about her sample from the first query that she overfits and chooses a second query that is very biased, for which the expectation of phi2 applied to her sample is far from its expectation over the entire distribution. Often, this requires a more clever approach for how to answer the queries. So for example, one such approach for SQs is this notion of a mechanism lying between Alice and the data set. And this mechanism adds some noise. So In this case, if Alice wants to know the value of some SQ phi, the mechanism takes her query, computes the empirical mean, but it obfuscates the result before giving it to Alice. So Alice will instead of getting the empirical mean, she gets the empirical mean plus some noise, where you can think of the noise as, say, Gaussian with mean 0 and an appropriately chosen variance. And this notion of a mechanism has been explored a lot in the setting of adaptive data analysis, where for different types of queries, you can potentially design a different mechanism that does well for that query. People have proven that this add noise mechanism, if you choose the noise distribution appropriately, can answer Q many SQs with only square root Q many samples. One thing to compare this to is a different approach where you take a separate sample for each SQ. And this approach, you can show that it works in an adaptive setting, but you need many samples to execute it. If you want a different sample for each SQ, well, you need 1 over epsilon squared samples for each query made. So you get Q over epsilon squared many samples rather than square root Q over epsilon squared many samples. Okay, so we now have kind of these two questions to think about for adaptive data analysis. And this brings us to the motivating question of our work. What sorts of minimal assumptions can we make about the queries to guarantee the responses will generalize even without an explicit layer between Alice and the data set? So even without like explicitly putting a mechanism between the two of them. Okay, and we give a solution that's pretty simple. It suffices for each query to take as input a random subsample of the data set and output few bits. And we're going to formalize exactly what this means in the sorts of guarantees we get in the coming slides. But before that, just a high-level outline of this talk. We're going to start by formalizing the guarantees we get for these things we coined subsampling queries. And if you're curious what this picture was on the cover slide, it's like a depiction of a subsample. You have a lot of food in a buffet, and you subsample some amount of it onto your plate. You're going to see, more accurate depictions of subsampling a data set on the coming slides, but here was just a cool-looking one to put on the cover. Once we have this high-level idea of what subsampling queries are, we're going to talk about some qualitative advantages of subsampling queries versus kind of like thinking about an explicit mechanism. And then we're going to give an example of where subsampling queries have a strong quantitative improvement on prior work. They give a simple and effective mechanism for SQs that is state-of-the-art in many parameter regimes. And then we're going to give some formal statements of our theorems that are like the previous ones will be a bit informal, but finally we'll formalize them. And I'm just going to give you one idea from the proof. Okay, so we start with formalizing this idea of a subsampling query. So such a query is defined by a function that takes as input a random subsample of the data. So think of W here, the size of the subsample it takes, as something smaller than N, the entire dataset size. And when Alice specifies this function, as a response, she gets just this query evaluated on a uniformly random subsample of the data. Okay, so it's like a very natural way of answering such a query. What we can prove is that if this query doesn't take as input too many distinct data points, and its range size is not too large, then even if we ask many adaptively chosen queries, assuming our data set size is large enough, these responses will generalize. Now, there's a couple of parameters here, so before I interpret this, I just want to eliminate one of them to make it a bit easier. We're not going to think about arbitrary ranges. For this talk, we're just going to think about 1 bit. So Alice's query will always output 0 or 1. And the high-level idea here is that whatever query Alice wants to ask that might require many bits, we can think of it as her asking a series of queries that each ask 1 bit. More formally, you're going to see examples later, such as the SQ mechanism, for which this 1 bit very naturally is what we want to do. Okay, so each subsampling query for this talk will take as input a random subsampling and output yes or no. And we can prove that the results will be representative, so every response to a series of Q adaptively chosen subsampling queries will be indicative of the true population, as long as the sample size is at least the size of each subsample times the square root of the number of queries. And you can compare this to a simpler approach where I take W different points for each subsampling query, or equivalently, I split a large sample into pieces of size W, which would work in terms of having guarantees for generalization, but requires a substantially larger sample. It requires linear NQ rather than square root NQ. So we get the same sort of improvement for these subsampling queries as were previously accomplishable for SQs. Okay, so now we've at a very high level talked about what our subsampling queries are, and we're going to move on to some qualitative advantages of this framework. The first qualitative advantage of subsampling queries is that many natural analyses are already subsampling queries. So let me give an example. Say I'm an analyst and I get a new data set that I know nothing about. The first thing I might do is pick 5 random points, infer some information about them, and from that information decide how to proceed, what other analyses to do. And this is exactly a subsampling query. The function mapping those 5 points to like what I have inferred is a subsampling query answered in the most natural way. Secondly, many algorithms already do subsampling kind of in their description. For example, something like stochastic gradient descent, at each step is picking a subsample and computing some information about it. So you don't need to imagine an additional mechanism. When doing many analyses or algorithms, they already fit within the subsampling-based framework. A second point I want to make is that this can handle an extremely broad class of queries. Essentially, anything you want to ask can be framed as a subsampling query, and it doesn't take much work to do so. So let me give an example of like a very complicated query. Say I'm a machine learning analyst, and I have a training set and a test set, and I want to get a sense for whether my training pipeline is accurate. So what I mean is, I'm going to take this training set, I'm going to learn some very complicated neural network, I might do some hyperparameter tuning, I might like look at them all and be like, I want to modify it a little here. Whatever I do, I'm like learning some model as a function of the training set. And then I'm going to measure its test accuracy, and I'm happy if I get more than 95% accuracy. Well, this entire pipeline is one query that takes as input number of points in the training set plus number of points in the test set and outputs good or not good. So it can all be phrased as one subsampling query and easily fit within our framework. In order to answer many such queries adaptively, I would want more than just strain plus test points. There's kind of no way to get around that. But assuming I have a large enough data set, I ask the query in the simplest possible way, and I can ensure that later analyses will still generalize. And a third point I want to make is this is kind of like more of trying to understand what the subsampling-based framework is doing. But one way to view it is it automatically designs the noise distribution. What I mean by that is for this example of statistical queries, we didn't want to give the true average. We wanted to add some noise to it, for example, a Gaussian with appropriate variance. But there are actually a number of different distributions you could use for the noise, and they have different pros and cons, and you need to calibrate the variance appropriately. And if I'm asking not SQs, but maybe some other weird query, I might want a different noise distribution. And one way to interpret our results is it's tailor-making a noise distribution for your query, and that noise is just the noise implicit in the subsampling process. So how different is my query on different subsamples? Now I, as a theoretician, don't need to think about how to design the appropriate noise distribution for my particular task at hand. I just do whatever subsampling does. Okay, so we've now talked about some qualitative advantages, and now I want to give you like a concrete quantitative application where subsamplings improve on prior work. This application will be to answering statistical queries. So say Alice wants to answer an SQ phi. And for now, we're going to assume that the range is just a single bit, 0 or 1. And in the next slide, we'll generalize this to the continuous range, 0 to 1. So to answer this SQ, well, phi is like already given as a subsampling query, right? It takes as input a subsample of size 1, and it outputs 1 bit. So we can ask that subsampling query. And Alice will get as response the function phi evaluated on a random point in the sample. So this is a 0, 1 bit with roughly the right mean. But its variance is kind of large. It's not gonna necessarily be close to the true mean. But it's very easy to decrease the variance. We just repeat this process k times and take the average of the k bits we get as a response. And via a standard Chebyshev argument, you pick k appropriately. This average will be close to the true mean with high probability. And if you notice what this is doing, this is answering the SQ in a very simple way. It's picking k random points from the sample, and it's computing the average of the SQ on those k points. And it uses that as its answer to the SQ, like a super simple mechanism that does quite well. If we want to generalize this to a continuous range, where now our range is the continuous interval from 0 to 1, we just cast that as a problem where the range is the discrete 0, 1 in a very simple way. We define a new SQ, phi prime, takes as input x, it computes phi of x, say that's 0.7, and then it flips a coin. 70% of the time it outputs 1, 30% of the time it outputs 0. And this is an SQ that has the same mean, but now it has the appropriate discrete range. And at this point, we do everything the same. We take a random input of s, we compute phi prime on it, we average all these bits, and we get a response that should be close to the true SQ mean. And it turns out this simple mechanism is state-of-the-art in a variety of parameter regimes. There are many different parameter regimes in which you can consider these mechanisms, and there are some where a different mechanism does a bit better, but for many, this is the best we know, exceeding prior work, and it's so simple. Okay, so now we've talked about the applications of our subsampling framework to SQs, and we're going to spend a little bit of time formalizing our theorem statements. And I just want to give you one idea from the proof that I can hopefully describe in just a couple of minutes, and then we're going to go to conclusion and potential future work. Okay, so to formalize our theorem, we need to formalize what it means to be low bias in the setting of subsampling queries. So say Alice asks these Q queries, and we want to ensure that all these responses, Y1 through YQ, are somehow low bias. But like each YI is just a bit, 0 or 1, and maybe like we want it to be something that's half the time 0 and half the time 1, so we can't just look at the value of Y. Instead, we need to look at its expectation. And we're going to compare two quantities. We're going to compare the expectation of Y after seeing the sample versus the expectation of Y on the distribution as a whole. So if I take Y on a fresh sample, what does it mean? And this kind of captures like how much is my sample S, how much does phi differ from the perspective of the specific sample S I have. And we prove that the expectation of the max error of any query you ask is bounded by this fairly simple function. It has two terms. The second term doesn't depend on the number of queries you ask, and actually doesn't depend on the adaptive setting at all. You can show that even if I ask a single query, I have some deviation from the mean of the points in S, and that term just captures what I call the implicit bias. The first term is the more interesting term. It's the bias due to adaptivity, which is as I ask more queries, how can I learn more about my sample and find more and more biased queries? And it has a fairly simple form here. It scales, square root with the number of queries I ask, and scaled by the size of the sample and the size of the subsamples used in each query. Okay, and furthermore, one setting that we care a lot about is when each query takes a subsample of 1 point, W equals 1. And this is a particularly important setting because it captures the mechanism we use for SQs, if you recall from a few slides ago, where we just looked at one sample at a time and computed a single bit approximating this SQ. And in this setting, rather than having a guarantee that holds an expectation, we can get one that holds with very high probability. So, if you took the expectation and you applied Markovs, you would get that as you decrease the failure probability, your guarantee gets worse in a kind of linear way. Here we get a logarithmic dependence. So you can make your failure probability exponentially small. And the term, we have this term here, that term is essentially corresponds to the expectation from the previous slide, and then we multiply by this logarithmic dependence on the failure probability. Okay, and I want to give you just 1 or 2 minutes about how this proof works without diving into details. The way we prove this is we first observe kind of like a simple way of decreasing the failure probability that applies in many settings, and maybe we can apply it here. And that is, so from the expectation, from the theorem on the previous slide, I know that with 99% probability, the analysis will have low error. But I want to improve this 99% to something very, very large. And the way I do this is I say, okay, if I do k independent analyses with very high probability, at least 90% of those analyses will have small error. Okay, so like kind of if I repeat the process a bunch of times, many of them will have small error. It might not be easy for me to tell which, so it's not clear that this is so useful in our setting, but it's a true observation. And then the idea is to imagine one interaction between Alice and the sample as k many roughly independent interactions. And the way we do this is we break the sample up into k many pieces, each with n over k points. And then whenever Alice asks a query, we look at, so the query is answered by taking a single point from the data set and applying phi to it. We look at which group that sample is, and then we assign it to kind of like a smaller Alice. So we're breaking Alice up into 3 pieces here. The first query is looking at the top subsample, so we assign that query to Alice 1, the second query to Alice 2, and the third to Alice 3. So whenever Alice asks a query, it gets kind of randomly routed to one of the Alices. And now we would love if like these Alices behaved independently. They do not, but we can show that the way they behave is in a formal sense no worse than independent. And once we show this, it implies that 90% of the groups will, with very high probability, have small error. There's a last step of how you go from this guarantee that 90% of the groups have small error to the entire sample having small error, which you don't want to just do the obvious thing because of just kind of like averaging their errors, because it could be the case that some of the groups have a lot of error. But if you're just do something a tiny bit smarter, you can show that, if you can guarantee that 90% of the groups have small error, then the entire sample must have small error. Okay, that was like a very quick overview of this particular aspect of the proof, how you go to very high success probability. I don't anticipate that that covers the whole proof, but hopefully it gives you a sense for what's going on. And I want to point out one thing, which is that this idea of error reduction only works when W equals 1, when every subsample takes as input 1 point. And the reason for that is whenever Alice asks a subsampling query, we want to route it to one of the groups. However, if the subsampling query takes as inputs 2 points, it could be the case that one of the points is in group 1 and one is in group 3, and it doesn't entirely lie within a group. So because of that, I don't know how to make this sort of error reduction work for larger W. Okay, at this point, I've covered the things promised on the outline, and I'm going to end with some high-level concluding remarks, both recapping what we did and also some future work. Okay, so to start with the recap, we defined this notion of a subsampling query and proved that with high probability, if an analyst asks a series of subsampling queries, all of the responses will have low error for some formal notion of error. And we also talked about, kind of at a more qualitative level, why this notion of subsampling query might be an appealing way to look at adaptive data analysis. So for future directions, I'm listing 2 here. One is kind of like a technical improvement, but I think you would have some cool insights if you can solve it, which is how do we get this very high probability guarantee even when we ask subsampling queries that take as input 2 or more points. And kind of the proof strategies that I know of break down in this setting, so I'd be very interested to see if someone can figure out how to handle this case. The second future direction is kind of much more high level, but I think one really nice thing about this entire work is that it looks at what analysts might already be interested in doing, and it argues that automatically leads to generalization even when they're doing this adaptively. So I'd be very interested if there are other ways to formalize kind of what are the things analysts might already be doing and prove that those formalizations also lead to generalization even in an adaptive setting. Thanks for listening to my talk. And if you have any questions, feel free to email me.